So let's talk about the forward probability. And we're going to show you how to compute the forward probability recursively. Here we assume we know the hidden Markov model parameter theta, which involves the initial distribution for Z1, not initial like the distribution for Z1, W, and the transition probability A, which describes the distribution among the Z's, and also the emission probability B, which describes the distribution between Z and X. So let's start with T equal to 1. So how we're going to compute R alpha sub 1 and I. By definition, it is a joint probability of observing data x1, and we also know that z1, the latent state, is equal to I. So how we compute this, the trick we will repeatedly use is basically the chain rule of a probability, meaning for any random variable x, y, z, the joint is always equal to the marginal of x and then the conditional of y given x, and then the conditional of z given all the previous random variables x and y. So this is the chain rule for probability, for joint probability. In this case, we have two random variables xi and z, x1 and z1. We start with the joint is equal to the marginal of z1 and then times the conditional of x1 given z1. So the first probability is the distribution for z1, so it's w evaluated at I, and then the second probability is emission probability. So that's the probability of, given we are at the latent stage I, what is the probability of seeing an outcome and x1. So we can compute alpha 1 and I. Suppose we have already computed alpha ti when t is equal to 1. So this is given. Now we wanted to compute the forward probability when t is equal to 2. By definition, alpha 2i is equal to the joint probability of observing x1, x2, and also the latent variable at time 2 is I. And we're going to compute that by adding back this latent variable z1 and sum over all its possible value, which is sum over j. Well, this is just because the marginal distribution of any random variable is always equal to a summation over j and p of x and y equal to j. So this is what we are doing here. The marginal is equal to summation over another variable z2. Now we have 4 random variables. Let's ignore this one at this moment. So we have x1, x2, z1, z2, and we're going to use a chain rule. And we start with x1, marginal of x1, z1, and then z2 given all the previous, which is x1, z1, and then x2 given all the previous variables. So it's going to be x1, z1, and z2. Now, I have some variables colored in gray. It just means that conditioning, that variable can be ignored. For example, for z2, when we condition on z1, z2 and x1 are independent of each other. So you can see that in the calculation for this conditional probability, we really don't need x1. Similarly, for x2, once we conditioning on z2, it is independent of z1 and x1, so we can ignore those in the computation. And you're going to find out this basically is the transition probability, and this is the emission probability B. So I want you to think about the hidden Markov model parameters as the following. We have the distribution W over the hidden states, which is a distribution for z1. So it's mz is a vector, probability vector of mz times 1. And the transition probability A is going to be a matrix mz times mz. And the ith row of this A matrix is the probability of going from, if your previous current state is I, what is the probability you're going to move to one of the MZ latent state at the next time point? And your emission probability B can be regarded as a matrix, which is MZ times MX. So it is this specifies the probability from Z to X. For example, for the ith row of B, that states the probability of seeing one of the X value, because there are M sub X different values, one of the X value conditioning on your Z is equal to I. So for this probability, we can just retrieve it from the A table, is the Jith entry. And for this probability, it is we just go to the B table and retrieve the corresponding entry in the ith row. Now for the first probability, this one is not, we cannot compute it directly from, this probability is not equal to any of those W, A, or B. But however, this is a quantity we computed before at t equal to 1. So this basically is equal to alpha sub 1 and j. So now we finish the computation for t equal to 2. It's a summation over j and of those products involving the calculation of the forward probability at the time t at time 1 and plus the transition matrix, some quantity from the transition matrix and some quantity from the emission matrix. Next, I want to explain why I draw the graphical structure of those three variables this way. This is the original graphical structure with 2 latent states and 2 observations. And now how to draw a graphical structure using only a subset of those variables. Here we only keep x1, x2, and z2, but we remove z1. And the graphical structure should be constructed in the following way. First, let's inherit whatever edges in the original graph. So in this new graph, we have to keep this edge. Why? Because in the original graph, we have an edge between z2 and x2. This edge means that z2 and x2 are dependent on each other, conditioning on given all the other variables, z1 and x1. So now if we move to a new graph, because we remove some variables, so we're actually going to condition it on less number of variables, meaning less number of information, then apparently z2 and x2 will continue to be dependent. So we're going to have this edge in the new graph. And next, we also going to add some edges in the new graph. For example, x1 and z2 in the original graph, they're independent because given z1, x1 and z2 are independent. But now in the new graph, because we remove z1, then x1 and z2 will become dependent, even conditioning on x2. So we have to add an edge between x1 and z2. And this is easy to understand. For example, suppose my z2 could be the block type of parents, and my x1 and z2 are block type of siblings. So apparently, if conditioning on the parents' block type, and the block types of siblings are independent, but if we remove without the information of the parents' block type, apparently the block types of siblings will be dependent. So this is why for the new graph, it looks like this. First, it inherits all the edges from the original graph, and also we add edges among pairs of nodes if they could be connected through some left out variables in the original graph. So in this case, x1 and z2 are connected, and by going through some variables which we're going to exclude in the new graph. So we're going to add an edge here. So this is a new graph, and for this new graph, how we work out the jointed distribution, which is our alpha, we factorize this way. So it's p of x1 z2 and then times p of x2 given all the others, but that only related to this edge, so it's x2 given z2. So this is basically the transition emission probability B, and we can directly grab from the parameter of a hidden Markov model. But the jointed distribution for this pair is complicated. We cannot directly grab it from either WA or B. Instead, and this, which is summation over J, this expression, which is basically our something involving our alpha and A, is the probability, joint probability for this pair, both x1 and z2. Next, let's continue with the recursive calculation. Suppose we have computed the forward probability at time t, and all the previous values are known. Now, how to compute the forward probability at time t plus 1? By definition, is equal to this. And so we're going to use the tricks we used before. First, we're going to write this marginal as a summation over another variable zt, so different value of zt, zt equal to j, we sum over j. So now we're working with this graph. And then we apply the chain rule. First is the marginal of this block of variables, is here, and then times zt plus 1 given all the previous variables, but that will only depends on zt. So that's this probability. Again, here I keep all the conditioning on all the previous variables, but if variables are in gray color, means it actually plays no role in this conditioning. And next, the last stage, we're going to calculate the conditioning of xt plus 1 given all the other variables, and you will find it only depends on the latent state zt plus 1. So the alpha is equal to a summation, and each term inside the summation can be break into a product of 3 terms. And the first term, which is the computation of this block of variables, it is difficult to compute, but luckily we have computed before. That's exactly alpha tj. And then this is our transition probability A. We can get it from the A table, and this we can get from the emission probability table B. So we are done. Now you can see how we calculate the forward probability. You can think about the alpha basically is a matrix with n times number of hidden states for z. So we first calculate the entries for when t is equal to 1. So t is equal to 1, which is this step. And then we compute t is equal to 2, which is this step, where when we do this computation, we have to use the calculation for the alpha from the first row. So we then we can sequentially doing this. We can go with our fill in the entries in the table at when t is equal to 3, where we have to use information from the second row, all the way until we fill in the row as the last row of this alpha table. So we are done with all the forward probability calculation.